All right. So right now, what we're going to be looking at is relations and functions. So relations and functions, as you know, this is a very interesting topic because you need to know it at C-Sec mathematics. You're going to need to know it if you go further to do additional mathematics, all right, which is all right, what this class is for, which is additional mathematics. And then you need to know it if you're going to pursue pure mathematics at Cape. And you also need to know it for, let's say you're going to try to go overseas, to go to university, you need to know this topic because it's also an SAT and ACT exams. So functions and relations, it has many applications to real life. And so let's dive into functions and relations. So now, what is a relation? So a definition of a relation is just a set of ordered pairs that obey a particular rule. That's a set of ordered pairs. So right here, I give you an ordered pair. We have -2, -1, -1, 2, 0, 5, 1, 8, and 2, 11. Those are called, those are the ordered pairs, right? So we have a set of ordered pairs. In the set of ordered pairs, we have -2, -1, 0, 1, and 2. Those are the first values in the ordered pairs, which we denote as the x values. And the x values are also called the domain. So the x values are called the domain. All right, so the set of elements of the ordered pair is called the domain and is usually represented by x. All right, these usually, when you're graphing them, go on the horizontal axis. All right, now the next one now is the second set of elements in the ordered pairs is called the range, and they're usually represented by y. Another graph, those go on the y values. Those go on the vertical axis. And so those y values are the vertical axis, the ones that go on the vertical axis, right? So now we put them together and we get our ordered pair. So now when we get our ordered pair, what you will find is that y is related to x, right? Where we can write y in terms of x. And since we can write y in terms of x, y obeys a particular rule of x, and then that is a relation. So y obeys a particular rule in x, and that's all a relation is. So look at this. In this example, the rule which governs the relation is x maps to 3x plus 5. So x arrow, so this arrow right here, that arrow right there means maps to 3x plus 5, which means x is mapped onto 3x plus 5. So what it means is that the y value right here that we get, it depends on x value such that the relationship which it maps onto x by is 3x plus 5. So for example, when x is going to be -2, when x equals -2, so right here when x is -2, so if you put in x as -2, you're going to get -1. Let's look at y. Y is going to be equal to 3 times the x value of -2 plus 5, because it's 3x plus 5 is the rule. That's what gives us our y value. And so 3 times -2 is -6 plus 5, which is -1. And so we have our x coordinate and our y coordinate. And then that gives us our ordered pair, -2, -1. You can go further now to when x is -1. When x is -1, what we're going to get is y is going to be equal to 3 times, of course, that -1. And your 3 times your -1, then you add 5. 3 times -1 plus 5. And what we get is -3 plus 5, which is 2. And so we can then say that our ordered pair right here is -1, 2, which is up there. All right. And so for each ordered pair in this set, so we have 1 ordered pair, 2 ordered pair, 3, 4, 5 ordered pairs. For each ordered pair, y is dependent on x and it is defined by the relation y equals 3x plus 5. And so we say x maps to 3x plus 5. Alright, and that's all a relation is. It's just a mapping. It's just a mapping from x to y. Most time they use x and y. The variables can change. Right? So it's just a mapping from one variable to another, and that's a relation. That's all there is to relation. Now, of course, there are going to be different types of relations. My apologies, I skipped all the way to the end. So, all right. So the next thing that we need to look at in relation is what is known as a mapping diagram. All right. So remember we said that x maps on to y. That's what we said. And so now we have the mapping diagram now, which is just a diagram which shows us what is really taking place for the set of ordered pairs. So usually some people like to draw like a circle, some people like to draw a square, right? I like to draw a square. So we draw like a rectangle or a square. And in the first square right here is for the x values. Let's write down our x values of -2, -1, 0, 1, 2. Alright, so that's the first square. In the second square, which is our 3x plus 5 value. And remember, 3x plus 5, this is our y value. X is being mapped to y. And so when x is -2, the corresponding y value was -1. When x was -1, the corresponding y value was 2. When x was 0, the corresponding y value was 5. When x was 1, the corresponding y value was 8. And when x is 2, the corresponding y value is 11. And so now we just draw an arrow from our x to the y, and we call that our mapping diagram. 1 maps to 8, 2 maps to 11. So this is then known as our mapping diagram. All right, and so a relation, sometimes they'll give you it as y equal to something y written in terms of x because y is dependent on x, or they can give you the relation as a mapping diagram. Now, relation can also be expressed graphically on a graph, right? So here's the relation rule, y equal to 3x plus 5. So there are going to be two axes. And so now, when you put it graphically now on a graph, so we have x and y. So of course, we're going to have two axes. We're going to have an x-axis and a y-axis. So this is just a rough sketch. It's not drawn accurately, but that represents our y-axis, the vertical line, and then the horizontal line is going to represent our x-axis. So what do we do after that now? After we draw our horizontal line and our vertical line, the x values are -2, -1, 0, 1, and 2. So it is -2, -1, 0, which is the origin, 1, and 2. Now the corresponding y values are when x is -2, y is -1. So let's put -1 right here. Then when x is -1, y is 2. So we got 2. So let's put 2 right here. That can be 2 on the y-axis. Then 5, we can put 5 up here. Then the next y value is 8, then 11. So I'm going to put 8 right here. And then the last y value is 11. All right, so when x is -2, y is -1. And so if you were to put it as a point, so remember each marking, so this is -2, right? And y is -1. So this is a point. So this point represents the coordinates when x is when x is negative 2 and y is negative 1. Now this is for when x is negative 1, y is 2, and so the corresponding point is this right here. And then when x is 0, y is 5. Then when x is 1, y is 8. And then when x is 2, y is 11. Now all of this can be represented by a straight line. Y equals 3x plus 5. As we know it, that's a straight line. Right? So my point is not drawn so properly. So I just have to do a rough sketch line. That should be a straight line, and this line would represent y equal to 3x plus 5. Alright? And that's the line y equal to 3x plus 5. Alright, so as we can just recall, so we can express a relation as a graph, we can express a relation as a mapping diagram, and we can express relation in terms of coordinates. Alright? So those are just how we can express relations. Now there are different types of relations, right? And there's also one special type of relation that is known as a function. So now, a function. What is a function? This is the big part of the topic, relations, right? So a function is defined as a relation where each element in the domain must map, but must map to only one and only one element in the range or the codomain. All right, so let me repeat that. So a function is defined as a relation where each element in the domain must map and map onto only one element in the range, and that is a function. So a function, as we just said, each element in the domain must map, right? And must map to just one thing in the range. So if you were to put a mapping diagram of what our functions represent, so let's go back around here. If you were to look at a mapping diagram, right, everything on the left-hand side right here must be going to something on the right-hand side. All right, and it must be going to only one thing on the right-hand side, and then we can say it's a function. So from this example, y equals 3x plus 5, clearly we can see that this mapping diagram is a function based on our definition. But let's look more into it now. So now, as we said, there's also some assumptions to make with functions. Whenever they don't tell you the domain, you're always to assume that the domain is x is an element of real numbers. Always assume that when they don't tell you the domain. But if I tell you the domain is it's integer, then the range is also integer. If I tell you the domain is whole numbers, then don't assume it's real or integer. All right, so when they don't tell you, you assume that it's real. All right, the next thing to look at is types of relations, right? Types of relations. So come off of functions just for a little bit. So types of relations. First, there's known as a one-to-one relation. What is a one-to-one relation? A one-to-one relation is where each element and domain is mapped and mapped only to one element in the range. And so we say that that is a one-to-one relation. So for example, f of x is equal to 3x plus 5. So sometimes you can see them write it this way, f colon x maps to 3x plus 5. This is the same as f of x equals 3x plus 5 or y equals 3x plus 5. This is a one-to-one relation. Why is it a one-to-one relation? Each element in the domain is mapped and mapped only once to one element in the range. So here's f of x equals 3x plus 5. So each element in the domain, so -2, -1, 0, 1, and 2, maps onto only one element in the range. So -2 maps to -1, -1 maps to 2, 0 maps to 5, 1 maps to 8, and 2 maps to 11. So each element in the domain maps to only one and only one element in the range. And so that is a one-to-one relation. And a one-to-one relation is a function. A one-to-one relation is a function because it satisfies the criteria to be a function. All right, now the next one to look at is a many-to-one relation. And a many-to-one relation is also a function. So let's look at what a many-to-one relation is. As you hear the word many-to-one, that means the many whole heap of the domain map to one sitting in the range. Many whole heap in the domain map to one sitting in the range. Or some people might look at it as many means more than one sitting in the domain map to one element in the range. And that's many-to-one. So consider a quadratic graph where we're looking at the mapping diagram for the quadratic graph for the domain where x is between -2 and 2. And so if the quadratic graph is x squared, look what happened. All right, so right here, we're considering the quadratic graph y equal to x squared. So you might see them write it as y equal x squared or f of x equal x squared. So if y equal x squared and they tell us the domain that we're using is x is between -2 and 2. So this is the domain, x is between 2 and -2. And so if I were to write down the ordered pairs, if I were to write down the ordered pairs, what I would get is this is the set that I would get. Alright, so the first one, when x is -2, what we're going to get is -2, and we'll square -2, we'll get 4. And so we'll get -2, 4. The next ordered pair that we would get is if I were to put in -1, what I'm going to get is -1 squared, which is 1. And then when I put in x as 0, then the corresponding y value is also going to be 0. Then if I were to put in x as 1, then the corresponding y value is also going to be 1. And then if I were to put x being equal to -2, not -2, +2, if I were to put x being +2, what I'm going to get is +2 squared is 4. And so this would give me the set of the ordered pairs. Alright, so now that I have the set of the ordered pairs, right? Now that I have the set of the ordered pairs, what do I need to do next? I'm showing you that it is many-to-one. So after I write the ordered pairs, I want to show you the mapping diagram. The mapping diagram gives you a clear indication of when it is many-to-one or one-to-one. Alright, so let's look at the mapping diagram. So I'm going to do the mapping diagram right here. The mapping diagram. Map diagram. I like to write acronyms, so I'm shortening it. Map diagram. So of course, we're looking at when x is mapped onto y and y is x squared. And so what I like to do is draw my box. Some people like to use circle, some like to use box or rectangle, some like to use square. Whatever you like to use, that is your preference. But the mapping diagram must just show what is being mapped to what. So x is -2, then we have -1, then we have 0, then we have 1, then we have 2. Now -2 is being mapped to 4, and so we can put a y value of 4. You're going to see why I put 4 down here. -1 is being mapped to 1, so I'm going to put 1 right here, and 0 is mapped to 0. So -2 is mapped to 4 right here. If I put my arrow right there, negative 1 is mapped to 1. 0 is mapped to 0. Now I'm going to change the color right here just to show you this. Now 1 is also mapped to 1 and 2 is also mapped to 4. Now look at this now. Negative 2 and positive 2, both of them map to 4. And so we have 2 elements in the domain mapped to 1 element in the range. So 2, that is many in the domain, mapped to just 1. So that's many to 1. All right? Many to 1. And so because it is many to, this is why it is many to 1. Now, a many to 1 is also a function. Why is a many to 1 also a function? Because each element in the domain map and it only map once. So look at it, negative 2 map to only one number 4. Negative 1 map to only one number 1. 0 map to only one number 0. 1 map to only one number 1. 2 map to only one number 4. And so each element in the domain maps and only maps once. And so we say that y equal x squared is indeed a function, but it is a many to 1 relation and it's also a function. So we just look at 1 to 1 function and now we look at a many to 1 function. All right, now let's say you wanted to sketch the graph of this or draw the graph. So you draw your y and your x-axis. This is just a rough sketch. And so drawing this graph, we shape it up. You're going to see why it looks like this, because when x is negative 2, the corresponding y value is 4. So let this be 4. So this is your point, negative 2, 4. When x is negative 1, your corresponding y value is 1. So let this right here be 1. When x is 0, then y value is 0. So this is the origin. This part is 0. When x is 1, your corresponding y value is 1. And then when x is 2, your corresponding y value is 4. So negative 2, 1, 0, and 2. And so this would represent how you would sketch or draw the graph of y equal x squared. So here's what it says. It says in the case of the quadratic relation above. So remember, we would have learned about quadratics earlier on, right? And in this case, in the quadratic relation, 2 different elements in the domain map to 1 element in the range, but each element is mapped onto 1 and only 1 element in the range. So this quadratic relation is many to 1 and is a function. All right, which is pretty much what I have said before that I rewrite right here. All right, that's it. So this is a many to 1 relation. Now there's next one other relation that we're going to look at, which is a one to many relation. So let's look at that, a one to many relation. A one to many relation. So a one to many relation. So let's look at an example to understand what is a one to many relation. And as the name suggests, one to many, it basically stating that one element in the domain map to more than one element in the range. So one thing in our domain, it map to 2 or more sitting in our range, right? So one thing in our domain map to more than 2 sitting in our range. All right, so just to put it in layman terms. All right, so one element in the domain maps to more than 1 element in the range. And so this is known as a one-to-many relation, and a one-to-many relation is not a function. A one-to-many relation is not a function because Remember what it says. It says each element in the domain must map and map to only one element in the range. So with a one-to-many function, it's already not satisfying the criteria to be a function, and it's not satisfying the criteria because one element in the domain is being mapped. One element in the domain is being mapped to more than one element in the range. But if it mapped to more than one thing, right, it automatically dissatisfies the function definition because the function definition states each element in the domain must map or only map once. So if this are mapped to many sitting already, it can't be a function, so it's just a relation, one-to-many relation. So let's look at this example. It says, consider now the relation x is mapped to the plus or minus the square root of x for the domain x is between 0 and 4. So the mapping diagram and the graph for the ordered pairs will appear. So let's let the mapping diagram appear. And so they already give us the ordered pair. So the ordered pair is 0, 0, 1, plus or minus 1, 4, plus or minus 2. So let me write it out what this really means. So ordered pairs, OP for ordered pairs. So writing it out, this is what we really have. When x is 0, y is 0. This is the first ordered pair. Then when x is 1, y is 1. Y is minus 1, that's 1, and y is also 1. So we get 1 minus 1, 1 and positive 1. Then when x is, this reach all the way up 4, but this is where x is between, so it skip out 2. I don't know why it skip out 2 and 3. So some of the ordered pairs are missing. When x is 2, then the result we're going to get is minus the square root of 2. That don't write good. We're going to get minus the square root of 2 and plus the square root of 2. So we're going to get minus the square root of 2. That's one ordered pair. And then we're going to get plus the square root of 2. 2 comma square root 2. Then when x is 3, let me make this a little bigger. When x is 3, what we're getting is, when we put 3 right here, we're getting minus the square root of 3. And then we're also getting plus the square root of 3. So we get 3, comma, positive root 3. Then finally, when we put x as 4, we're going to get this minus the square root of 4 is negative 2. And so we get 4 negative 2. And then when we put this right here, which is plus the square root of 4, we're getting positive 2. So we get 4, comma, positive 2. Alright, so that's what we get. Alright, so now that we've gotten that out of the way, so we've got our ordered pairs, then the next thing we need to do is to draw our mapping diagram. So I like to draw a box. I'm going to just put a box right here. And then I'm going to put another box right here for the range. And so the corresponding x values are 0 to 4. So we have 0, 1, 2, 3, and 4. Now the corresponding y values are 0. I like to do it in order. And so the corresponding y values are, I'm going to start from the most negative, which is negative 2. I see negative 2. Then I have negative the square root of 3. Then I have negative the square root of 2, then I have -1, then I have 0, then I have +1, the square root of 2, then the square root of 3, and then 4. Not 4, 2. Square root of 4 or 2. And so I like to write them in ordered pairs. And so now, watch what happened. 0 maps to 0, right? 1 is being mapped to -1 and 1. So 1 is being mapped to -1 and 1 is also being mapped to 1. So I use a different color to show that 1 is also being mapped to 1. Now 2 is being mapped to negative the square root of 2, and 2 is also being mapped to minus the square root of 2. So it's being mapped to the square root of 2 and minus the square root of 2. 3 is being mapped to negative root 3, and it's also being mapped to positive root 3. And then 4, finally, 4 is being mapped to -2, and 4 is also mapped to 2. And so as you can clearly see, each element in the domain maps, but it maps twice, because 4 are mapped to -2 and 2, and 4 are mapped to 2 and -2, 3 are mapped to negative root 3 and root 3, and so each element maps more than once, and so it is not a function. So a one-to-many relation is not a function. All right, a one-to-many relation, not a function. All right, so let's say we wanted to sketch the graph. So you draw your x and your y axis. And so you start with 0, 0. Then you have when x is 1, you get y is equal to 1, and also y is equal to -1. So this is when x is 1. Then you have when x is 2, you're going to get negative the square root of 2, positive the square root of 2, all the way to 4. Then when x is 4, we're getting a y value of 2 and -2. And there's a reason why I skip out 2 and 3, right? Because it's 1 point something. The square root of 2 is 1 point something, 1.4, and the square root of 3 is 1 point something, I think 1.73. All right, so they'll fall in between these values, between 1 and 2. So when y is 1, we're going to get, when x is 1, y is 1, and when x is 1, y is also a -1. And so the first part, it looks something like this. We're connecting it. When x is 4, y is 2, and y is also a -2. So if you continue, this is the graph of y equal to the root of x, plus or minus the root of x. I have to write that part, plus or minus. So when x is 4, y is 2, or -2. When y is 3, when x is 3 rather, y is root 3, which is 1.73, or y is -1.73. When x is 2, the corresponding y value is root 2, which is 1.41, or -1.41. When x is 1, y is 1, or y is -1. And so that's the graph of y equal to the square root of x, and it's plus or minus the square root of x. And so a one-to-many relation is not a function. A one-to-many relation is not a function. All right. So in this case, each element in the domain is mapped to 2 elements in the range. And so the relation x, which maps to plus or minus the square root of x, is not a function. That is, a one-to-many relation are not functions. Now, Here's a quick way how you can determine if it's a function. Let's say you don't want to use the mapping diagram. The mapping diagram will show you if it's a function, right? Where you just need to check if each element in the domain maps or maps only once. So those are the two criteria you check for if it's a function. You check if each element in the domain map or if it map only once. Now instead of using a mapping diagram, you can use a graph. And to use a graph, we use what is known as a vertical line test. So a vertical line test is used to determine if whichever graph we get, if it's a function. Now what the vertical line test says is that if we can draw a vertical line and it detects only one point of intersection with the vertical line, then it is a function. Otherwise, it is not a function. All right, so let's go back to this example right here. So what we're basically saying is if we draw a vertical line, anywhere on the graph, we should only get one point of intersection. Right here, when I draw the vertical line, I am getting 2 points of intersection, which is more than one. And so we could conclude that hence this is not a function. So this is not a function, not a function, right? Not a function. That's from vertical line test, not a function. So once the vertical line detects more than 1 point, it's not a function. All right. Let's go to the graph of y equal x squared. Anywhere on the graph right here, let's say we draw a vertical line. So if we draw a vertical line anywhere on the graph, it's only going to have 1 point of intersection. Now, remember this line right here, we can always move it, right? So look, another vertical line, only 1 point of intersection. Anywhere on the graph we move the vertical line, it only have 1 point of intersection. That 1 point of intersection is right here in this case. And so what we then say is that y equal x squared is a function. All right. So we can use vertical line test to determine if we have a function, yes or no. All right. Again, this relation where we had y is 3x plus 5, we could draw a vertical line. And on the vertical line, we're only going to have 1 point of intersection, right? And so clearly we can say that y equal 3x plus 5 is a function. All right. So now that we've looked at what a relation is, and we define a relation as a mapping from one variable to another that obeys a particular rule. We've also looked at the definition of a function, and that a function is a special type of relation where each element in the domain map are only mapped once. Then we look at the types of relation where we have the types of relation where we say we have one-to-one, one-to-many, and many-to-one. We said that a one-to-one is a function, a one-to-many relation is not a function, and a many-to-one relation is a function. So that's a review so far of what we've done. All right. All right. Now that we've looked at so far functions and relation, the next thing to talk about with function is known as the inverse of a function. All right. So everything always have inverse, right? So the inverse of a function. What's an inverse? So the inverse of a function f is defined as f raised to the power -1. So this weird thing here right here is raising to the negative power. And it's a function that will map the range of f back onto the domain of f. This is obtained by interchanging x and y elements of the ordered pairs. And so if the function f of x is 3x plus 1, where the ordered pairs is -1, -2, 0, 1, 1, 4, 2, 7, then the inverse will become we're going to interchange x and y. So the ordered pairs for f inverse becomes -2, -1, 1, 0, 4, 1, and 7, 2. So now look carefully at this function. We have f is -1, -2. And for the inverse of this function, we have -2, -1. So for the inverse, all we do is interchange x and y for the ordered pairs. Alright? And so for the inverse function, when you do it in a mapping diagram, you just, instead of mapping the domain to the range, this time we're going to map the range back onto the domain. That's the inverse. Alright? Now here's the final thing we need to know about inverse. Since the inverse has to be a function itself, only a one-to-one function can have an inverse. So now only a one-to-one function can have an inverse. Alright? We're going to prove why that is so later on. Right? We're going to prove why only a one-to-one function can have inverse. Right? Later on. But because a one-to-one function now, a one-to-one function, it is able to easily map, it only map from one element in the domain to one element in the range. So it becomes easy to map back the range back onto the domain because it only map to one thing. And so clearly we can see why a one-to-one function will have an inverse. Now later on we'll disprove why the others don't have an inverse, but just know that for now. Alright. So now, how do we go about finding the function f inverse of x now? So let's look at that. So we said that right here. So our inverse is if we have a function f of x, so we say in this case f of x is 3x plus 1, right? And so this is the function f of x. As an ordered pair, we write it out and we're getting when x is -1, we get 3 times -1 plus 1 is -2. When x is 0, we get y is 1. When x is 1, we get y is 4. Then when x is 2, we get y is 7. Right? And so that gives us f. Now, what we need now is f inverse. So we need to find what is f inverse of x. How are we going to find what is f inverse of x? Right? That's what we need to find. But we know what f inverse of x will be as an ordered pair. It's just the interchange of x and y. So it is -2, -1. Then it becomes 1, 0. Because we're interchanging x and y to find the inverse. Then it becomes 4, then 1, and then this becomes 7, 2. 7, 2. And so then that gives us f inverse. Now after we get f inverse, right? So after we get f inverse, in terms of an ordered pair, how are we going to get the function f inverse of x? So let's look at how we get the function f inverse of x. To get the function f inverse of x is pretty simple. Alright, so let's look at how we do that. So to find f inverse of x, first thing we do, we interchange x with f. Remember, f really means y. So sometimes say y or x. So first and foremost, step 1, f of x is 3x plus 1. So this is the same as saying f of x is y. So this is the same as writing y is equal to 3x plus 1. So that is step 1. Right? So step 1, you write y equal 3x plus 1. Step 2 is you interchange x and y. So step 2, you're going to then write x is equal to 3y plus 1. You interchange x and y. So this is step 2, you interchange x and y. So that is step 2, interchange x and y. After you interchange x and y for step 2, right? So we interchange x and y for step 2. Step 3 is make y the subject. Make y subject again. So you're going to make back y the subject. Make y the subject. So to make y the subject, this is what we do. So we have x equal to 3y plus 1. So what we get is, to make y the subject, we subtract 1 from both sides. So we get x minus 1 is equal to 3y. And so then we divide both sides by 3 to get y would be equal to x minus 1 over 3. Y would be equal to x minus 1 over 3. Now this y that we get, we're going to step 4 now, write y as f inverse of x. So write that this new y that we get, write y as equal to f inverse of x. And so that is the inverse. So we're done. So this implies that f inverse of x is equal to x minus 1 over 3. X minus 1 over 3. Now pre this, so look at this now. Since we said that f inverse of x is x minus 1 over 3, look at this. X minus 1 over 3. If you put x as negative 2, you get negative 2 minus 1 divided by 3, which is negative 1. Aha, see it there? If you put x as 1, you get 1 minus 1 is 0. 0 over 3 is 0. Nice. If you put x as 4, you get 4 minus 1, which is 3, and 3 divided by 3 is 1. If you put x as 7, you get 7 minus 1, which is 6. 6 divided by 3 is 2. And so no matter the x value, we notice that we get the corresponding y value. And so this is indeed true, that in order to find the inverse, we have to interchange x and y, then make back y the subject. That's how you find the inverse function of x. So here, if f of x is 3x plus 1, then the inverse of x is x minus 1 over 3. So just to practice some more, let's try to find some inverse function. Oh, before we can practice some more, it's very important to observe this. So I'm just going to write back down f of x right here. There's something that I really want us to master right here. If we're just going to look at the mapping diagram for the function, right? So let's look at the mapping diagram for the function. So we have x is mapped to, so we see that x is mapped to 3x plus 1. X is mapped to 3x plus 1, right? So this is x, and it's mapped to the function y, which is 3x plus 1. Let's draw our box right here. We'll draw another box right here. So all of the x values that we did use were negative 1, 0, 1, and 2. So negative 1, 0, 1, and 2. Negative 1, 0, 1, and 2. Now when x was negative 1, we got negative 1 times 3 is negative 3 plus 1, which is negative 2. And so negative 1 maps to negative 2. When x is 0, we get y is 1. And so 0 is mapped to 1. When x is 1, y is 4. And so 1 maps to 4. And then when x is 2, y is 7. And so 2 maps to 7. Now this is the function f. So it undergoes the function f. Now in order to find the inverse relation now, So this is the domain. So remember, this is domain. X is your domain, and 3x plus 1 is your range. Now what the inverse does, it maps the range back onto the domain. And so this is what the inverse function does. The inverse function maps the range back onto the domain. So this is f inverse. The inverse function maps. Alright, and so the inverse function, what it does is it maps the inverse function, it maps the range back onto the domain. That's what the inverse function does. So the arrow is going to point in this way, where I map the range. So it's going to map -2, and -2 being mapped onto -1. 0 is being mapped, not 0, 1 rather. 1 rather is being mapped to 0. One rather is being mapped to 0. 4 is being mapped to 1, and 7 is being mapped to 2. So of course we can then make some conclusions about the inverse of a function. So this is the domain, and this is the range. So the domain, this is the range. So the conclusions that we can make is that the domain of the inverse function, the domain of the inverse function is equal to the range of the original function, and the domain of the original function is equal to the range of the inverse function. So here it is, the range of f, the domain of f is equal to the range of f inverse, and the range of f inverse is equal to the domain of f. Now, the inverse of a function and a function itself, they obey a particular relation such that if you were to sketch the graph of y equal f of x and sketch the graph of y equal f inverse of x, they are related together by being reflections through the line y equal x. So they're both a reflection of each other. So if you sketch both of them on a graph, you're going to find out that when you sketch both of them, they are a reflection in the line y equal x. So if you remember from coordinate geometry, we know how to sketch the equation of lines, right? So let's go back to this one. f of x equal 3x plus 1, and f inverse is x minus 1 over 3. So if we were sketching the graph, I don't have much space right here, but sketching the graph of 3x plus 1, it has a gradient of 3 and it passed through the y-intercept of 1. And so the graph would look something like this. That is a graph of y equals 3x plus 1. It has a positive gradient of 3 and it passes through the y-intercept of 1. So this is y equal f of x. So this is f of x. Now for the inverse function now, the inverse function has a gradient of 1 over 3 and passes through minus 1 over 3. So the inverse function has a gradient of 1 over 3 and passes through minus 1 over 3. So that would look something like this. So the red line is going to be for the inverse function. So it passes through minus 1 over 3. Alright, that looks like minus 1 over 3. So that's just a rough sketch. So this would be the graph of f inverse of x. And it passed through right here, the y-axis intercept is minus 1 over 3. Alright, now both of these are a reflection of each other through the line y equal x. Alright, so therefore to solve To solve or to find the point of intersection where a function and its inverse intersect, we solve f of x equal x, or we solve f inverse of x equal x, because they both intersect through the line y equal to x. So we look more at this when we're looking at some examples. So right here it says find the inverse of the following function. It says g of x is 3x plus 2. So find the inverse of the function. I don't want a mapping diagram and I don't want no graph. I just want to find the inverse. So the first one, g of x equal to 3x plus 2. Alright? So g of x is equal to 3x plus 2. G of x is 3x plus 2. So remember, step 1, you're going to write g of x as y. And so y equal to 3x plus 2. That is step 1. Then what is step 2? Step 2, interchange x and y. And so we have x is equal to 3y plus 2. Then step 3, make y the subject. And so we get x minus 2 is equal to 3y. And so all we need to do now is divide both sides by 3. So divide both sides by 3. And so what we get now is y is equal to x minus 2 divided by 3. Y is equal to x minus 2 divided by 3. And so this 3 cancel this 3. Y equal x minus 2 over 3. And so then we'll rewrite this y step 4 as g inverse of x. And so to finally finish it, we have g inverse of x is going to be equal to x minus 2 over 3. X minus 2 divided by 3. That's g inverse of x. Now let's look at the second example. The second example is a bit more challenging because it's a rational function, and it tells us that f of x is equal to 4x plus 5 over x plus 2. So it's equal to 4x plus 5 divided by x plus 2. F of x is 4x plus 5 divided by x plus 2, so that is f of x. So now we need to find out f prime of x. So the first thing is that we're going to rewrite f of x as y, and so y is pretty much equal to 4x plus 5 divided by x plus 2. That is step 1. I love when we write down the steps. You can never go wrong with the steps. So step 2 now is that we're going to interchange x with y. And so this implies we have x is equal to 4y plus 5 over y plus 2. So we have 4y plus 5 over y plus 2. Now step 3, make y the subject. How are we going to make y the subject? This looks pretty weird, don't it? To make y the subject. Now this is easy to make y the subject. All you have to do now is think of this as x over 1. So if we cross multiply them, we would get x times y plus 2. X times y plus 2 is equal to 1 times 4y plus 5. 1 times 4y plus 5. So that's what we get. And so now all we need to do now is multiplying x times y plus 2 right here. And so what we get is xy plus 2x, xy plus 2x, alright, so that's how we would find fg of x. Now what if we were to find g f of x? G f of x. So to find gf of x, think of this f of x as a x. This f of x becomes your x. So put f of x into g. So what is g of x? G of x is 3 times your x. Your x in this case is going to be f of x. So it's 3 times f of x plus 2. So it's 3f of x plus 2. So that's equal to 3 times what is f of x? F of x is 2x minus 1 plus 2. And so your gf of x works out to be 6x minus 3 plus 2. And this simplifies down to be 6x minus 3 plus 2 minus 3 plus 2. What is that working out to be? That appears to be negative 1. So what I want you to observe, however, the key thing to point out is that gf of x is not equal to, fg of x. Gf of x is not equal to fg of x. That's what we point out. Gf of x is not equal to fg of x. And so that's it. And that's pretty much what you need to know to derive composite functions. So here is another example. It says let f of x be equal to 2x plus 5 and g of x 3x minus 1. Find fg of 2 and gf of minus 1. So find fg of 2 and gf of minus 1. So there are two ways you can do both of these questions. So I'm going to put a line. On the left hand side we'll work question 1 and on the right hand side we'll work question 2. So for the first one, they want fg of 2. So the first thing you can do is find g of 2. And so g of 2 is going to be equal to 3 times 2 minus 1. 3 times 2 minus 1 is 6 minus 1, which is 5. And so g of 2 is 5. And so what we can write then is f g of 2, but g of 2 is 5. And so what we're finding is f of 5. And so f of 5 is then equal to 2 times 5 plus 5. And 2 times 5 plus 5 is 15. And so fg of 2 is equal to 15. Let's look at the alternative method. Alright, or. So now we want to find fg of 2. So what we can do is first we're going to find fg of x. So first we're going to find fg of x. Fg of x is equal to, we're going to put g of x into f. And so it's going to become 2 times g of x plus 5. That's fg of x. We replace x with g of x. 2 times g of x plus 5. Now g of x is 3x minus 1. So it becomes 2 times 3x minus 1. 2 times 3x minus 1 plus 5. And so what this is simplifying to be is 2 times 3x is 6x. 2 times minus 1 is minus 2 plus 5. Minus 2 plus 5 is 5 minus 2, which is plus 3. So that is fg of x. And so therefore fg of 2 is, we can replace x with 2. Fg of 2 is equal to 6 times 2 plus 3. 6 times 2 plus 3. And 6 times 2 plus 3 is 12 plus 3, which is 15. And so that gives us fg of 2. So notice there are two ways. We could have found g of 2 first, and then the result is 5. And so fg of 2 is then the same as f of 5, because g of 2 is 5. then that gives us the answer. Or we could have found the composite function fg of x and then plug in x as 2. So the same way we can do it over here for g f of minus 1. So method 1 is we can find f of minus 1, and f of minus 1 is going to be equal to 2 times minus 1 plus 5, 2 times minus 1 plus 5, and 2 times minus 1 plus 5 is minus 2 plus 5, that looks like 3. And so after we get f of minus 1 is 3, what we then go ahead to find is to say that g f of minus 1 is going to be equal to f of minus 1 is 3, and so what we're finding is g of 3. Then g of 3 is just going to be 3 times 3, replace x with 3, minus 1. And that is 9 minus 1, which is 8. And so that gives us g f of minus 1. After we get g f of minus 1, then what we're going to need to do is, this is the answer, g f of minus 1 is 8. So g f of minus 1 is 8. The alternative method would be to find g f of x. So we need to find g f of x. To find g f of x, that would be equal to g, we're putting f of x into g, and so it would become f of x is 2x plus 5, so it is 3 times f of x minus 1. 3 times f of x minus 1, which is 3 times f of x is 3x minus 1. So it's 3 times 3x minus 1. Wait, f of x is not 3x minus 1. F of x is 2x plus 5. So that's 2x plus 5. And then we're subtracting 1 from it. And so what we're getting is 3 times 2x is 6x. Then 3 times 5 is 15, and 15 minus 1 is 14. So we get 6x plus 14. And so what we get then is g f of minus 1 then is going to be 6 times minus 1 plus 14. So 6 times minus 1 plus 14. 6 times minus 1 plus 14, that's equal to negative 6 plus 14, which is 8. So either way you do it, the result is 8. Alright, so those are the two methods you can use to derive the solutions for composite functions. The next thing we need to talk about is, you have what is called rational functions. We looked at an example, but we're going to go more into them. And we're going to look at when is a function undefined, and it's usually for rational functions. Oh, we have some more questions to do first. Okay. So this question says, given that the function f of x is 2x minus 7 over x plus 1, and g of x is the square root of x plus 3, find g of 6, fg of 6, f inverse of minus 1, g inverse of minus 1, and gf of x. So that's what they asked us to find. Find g of 6. So for the first part, I'm going to put a line right here. So the first part, let's find g of 6 first. So g of 6, that's going to be equal to the square root of 6 plus 3, because x is 6. 6 plus 3. And so g of 6 is equal to the square root of 9. And with square root 9, we get plus or minus 3. Now always remember this, when you square root a number, you get two answers, plus or minus. So the square root of 25 is plus or minus 5. The square root of 49 is plus or minus 7. When you square root a number, you get plus or minus. Easy. The next thing is that it asks us for is fg of 3. Fg of 3. So we want fg of 3. So to get fg of 6 rather. So fg of 6. Now, given that we already find g of 6, which is 3, and so fg of 6 is just going to be equal to f of 3, and f of 3 is equal to, now you're wondering why I didn't take the minus 3, right? Now, this question right here, I can assume that they want the positive value. Why can I assume that? Is because generally when they want the negative value, sometimes they'll tell you plus or minus the square root of. But given that they didn't tell me plus or minus the square root of, even though I know that g of 6 will give me two values, I can assume that the same g of 6 value I will use here is the positive value. Right? Because they didn't give me a minus 1 right there or a plus right there. So f of 3, right, because g of 6 is 3, so f of 3 would be 2 times 3 minus 7, 2 times 3 minus 7 over 3 plus 1. So this works out to be 6 minus 7, which is negative 1, over 3 plus 1, which is 4. So fg of 6 is negative 1 over 4. Alright? Now, next thing it asks us is find f inverse of negative 1. So we need to find f inverse of negative 1. Before we can find f inverse of negative 1, we need to know what is f inverse. Right? What is f inverse? So f of x is 2x minus 7 over x plus 1. So let's write that down. So we're at this part now. Right? So we have f of x is equal to 2x minus 7 over x plus 1. So now that we have this as f of x, then what that is telling us then is we can replace f of x with y, and so we're getting y is equal to 2x minus 7 over x plus 1. That is y. 2x minus 7 over x plus 1. And so after you find this now, let's bring it up here. So y is y. Then we're going to interchange x and y, and so we get x is equal to 2y minus 7 over y plus 1. Then what is step 3? Step 3 is to make back y the subject. And so from right here, so we get x times y plus 1. X times y plus 1 is equal to 2y minus 7. 2y minus 7. So what are we getting now? So this works out to be x times y plus x is equal to 2y minus 7. So remember, we need to make y them there on one side, so we'll factorize it, we'll only have y on one side, right? Because we want y in terms of x. So we're going to bring over the 2y over here, so we'll get xy minus 2y is equal to, we bring over the minus x over there, so to get minus x minus 7. So we can factor out the y now, factor out the y, and so we get factor out y, and I'm getting x minus 2 is equal to negative x minus 7. So if I divide by x minus 2, I'm getting that y is equal to minus x minus 7 over x minus 2. Easy, 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 easy question. Right? That's what I get for y. And so now we can find f inverse, because remember y, replace y with now f inverse. So this is f inverse of x. And so y is f inverse of x. And so f inverse of 1 is going to be equal to negative 1 minus 7 over 1 minus 2. And so this works out to be negative 8 over 1 minus 2 is negative 1. And so f inverse of 1 is 8. F inverse of 1 is 8. Alright, easy. Now, what are we going to do next? We need to find g of 1. Right? So we need to find, well, g to the minus 1 of 1. So we need to find the inverse function of g and then find g of negative 1. So let's do that. Right? Oh, mistakenly take away the question, but I remember what the function was anyway. Alright, so anyways, the function g of x was the square root of x plus 3. That's g of x, right? And so what we can then say then is replace g of x with y. So replace g of x with y. And so what we get then is y is the square root of x plus 3. And so x is equal to the square root of y plus 3 because we interchange x and y. So to make y the subject, we can square both sides to get x squared is equal to y plus 3. We have to square both sides. Then we can subtract 3 from both sides to get y would be x squared minus 3. X squared minus 3. After we get y, this y is now our g inverse of x. And so g inverse of x is x squared minus 3. And so what we can then say then is that g inverse of negative 1 is going to be equal to negative 1 squared minus 3. Negative 1 squared minus 3. And negative 1 squared is 1, and 1 minus 3 is negative 2. And so that gives us g inverse of negative 1. Easy, easy, easy questions. Easy, soft. Alright? So now, next thing to look at is one more question. It says the diagram below is a sketch of the function f of x equal to the root of x for the domain where x is between 0 and 4. Redraw the sketch and show the inverse function f of x and draw the line which represents the relationship between f of x and f inverse of x. So then give me this graph right here, right? Then give me this graph right here and ask us to find the inverse functions first. So first and foremost, you can write y is equal to the root of x, right? Because remember, f of x is y, so rewrite y as f of x step 1. So the next step is to then say x is equal to the square root of y. So interchange x and y. So to make y the subject, what we can then do is square both sides. So that arrow implies x squared is equal to y. Now this new y that we get, it is f inverse of x. And so f inverse of x is equal to x squared. F inverse of x is x squared. And so all we need to do is to construct the graph of x squared. And that's going to be the inverse function. Alright, and so what we have, this is our x-axis, this is our y-axis. They say redraw the sketch. This is 0, this is 4, this is the curve. Alright, this is the curve of this right here. This curve from 0 to 4 is y equal to root x. And then the inverse function, wait, this is the point 2. Then the inverse function goes something like this. And this will be the graph of y equal to f of x. And this f of x in this case is x squared. So this is where y is equal to x squared. So let me write this better. This is the graph of y equal to x squared. Or I should have just erased it. Alright. Now how do I know this is a sketch of y equal to x squared? Y equal to x squared is just a quadratic graph, right? That shapes like this. Simple as that. Alright? I want to give a better sketch. I really do. So I'm going to give a better sketch. So I'm just redrawing it so it looks better. So it looks more accurate. So the first thing is I'm going to use different colors this time. So we have y equal x squared. That's y equal x squared. Right? Really want it to be accurate. Alright, that's y equal x squared. This is when x is 4, the corresponding y value is 2. That's y equal x. That's y equal root x. Y equal root x. Because the square root of 4 is 2. Now I'm going to use the color red now to draw the graph of y equal x squared, which is the inverse function of f of x. So this y here is really f of x. So you can go ahead and write that too. That's your function f. This is your function f. And then now I need to sketch f inverse. Now this is when x equal 2. When x equal 2, x squared is going to give me 4. So I can put 4 right here. Right? And so when x equals 4, x squared is 16. So the quadratic curve is going to look something like this. Going all the way up, up, up. Alright, this is 4. And continue. So that's a graph of y equal to, this is the graph of y, which is f inverse of x, and this is equal to x squared. Then finally, it says, and draw the line between f of x and f inverse of x. The line between them is y equal to x. So we draw a line, this line right here. It represents the color. It represents the line y equal to x. That's the line y equal to x. What's the relationship between the two? They are inverse of each other. Alright, so you can write that they are inverse of each other. Right? The relationship between the two lines is that they are inverse of each other. What does that mean? They are a reflection in the line y equal x. So you write that down. So y equal f of x is a reflection y equal f of x is a reflection of y equal to f inverse of x in the line. This is a relationship for us stating in the line y equal to x. Easy question, soft. That's it. So now we're looking at using inverse functions to solve any question. So now listen what this rule says. It says if f of x is equal to n, then x is equal to f inverse of minus 1 of n. And also if f inverse of f of x is equal to x, we can use that to solve questions. So for example, it says given f of x is equal to 4x plus 5 over x plus 2, find f inverse of x and then hence solve 4x plus 5 over x plus 2 equal 3. So now it says hence, so we have to use this. So we're using the inverse to solve questions. So what this rule is saying right here, think about it. So if I tell you if f of 0, this is just an example, if f of 0 is equal to 2, then this implies that f inverse of 2 is equal to 0. Right? Because remember we said that we interchange x and y. That's what the inverse function do. And so if f of 2 equals 0, then f inverse of 2 must be equal to 0. Alright. So now let's use this idea to solve the question that they gave us. So the question that they gave us, they told us that f of x is 4x plus 5 over x plus 2. So f of x is equal to 4x plus 5, 4x plus 5 over x minus 2. That is f of x. F of x is 4x plus 5 over x minus 2. So then now the question says find f inverse of x. Now we did find the inverse function for this question long time. So remember when we said f of x was 4x plus 5 over x plus 2, the inverse was 5 minus 2x over x plus 4. 5 minus 2x over x plus 4. It's the same question. And so right here, the same question, right? And so the inverse is just going to be the same as around there, which was 5 minus 2x over x plus 4. So f inverse of x is 5 minus 2x over x plus 4. That's the inverse function. So after we have the inverse function now, it says hence use the inverse and solve 4x plus 5 over x plus 2 equals 3. So right here, so what they're telling us that f of x equals 3. So solve f of x equals 3. So if f of x equals 3, this implies that x is equal to f inverse of 3. That's what they're telling us. So x is equal to f inverse of 3. Right? And so what we can then state then is that f inverse of 3 is going to give us x. So f inverse of 3 is going to be equal to 5 minus 2 times 3 over x is now 3 which is 3 plus 4. And so what we're getting is 5 minus 2 times 3 is 6. 5 minus 6. 5 minus 6 is negative 1. And this is over x plus 3 plus 4, which is 7. And so f inverse of 3 is equal to negative 1 over 7. Alright? And so therefore, f of x equals to 3. Solving f of x equal to 3 implies x is equal to negative 1 over 7. Now let's verify this answer. So to verify this answer, we're just going to solve this equation equal to 3 straight away. So let's say we wrote down 4x plus 5 over x plus 2, and we're solving this equation equal to 3. So what we do is we cross multiply to get 4x plus 5 is equal to 3 times x plus 2, which is 3x plus 6. And so solving this now, what we're getting would bring 3x over here to get x, and we'd bring 5 over there to get 1. So this is telling me that x should be equal to 1. So how did I get minus 1 over 7 here? So let's look back at the inverse function. So this is how you can know to verify your answer. So clearly something went wrong right here. Now what went wrong? Let's go back and check. Did I write down the correct inverse function? The inverse function should be 5 minus 2x over x plus 4. That's the inverse function. 4x plus 5 over x plus 2. So here's a mistake from all the way around here. So right here, when you bring over the 4y, it becomes minus 4y. And so when you divide it, you're dividing by x minus 4. And so the inverse should actually be x minus 4 in the denominator. Nice, right? So I made a simple mistake right there. So let's go back around here now. So the inverse should have actually been x minus 4, x minus 4. And so this becomes minus 1 over negative 1. And minus 1 over negative 1 is 1. And indeed, it implies now that x equal to negative 1. So now we verify that the two methods is correct. Alright? So whenever you're solving f of x equal n, so let's go back to the rule. This is the rule. Whenever you're solving f of x equal n, so anytime you solve f of x is equal to n, anytime you solve f of x equal n, it is implying that you can solve f inverse of n, and that will give you x. Alright? That's the rule. Easy question. So we're just using inverse to solve equations. Alright, now deriving composite function. Sometimes you can be given a composite function and asked to derive the two functions from that composite function. So what you're going to have to do is find the inner function and then find the outer function. So let's look at how we do that with an example. For example, right here it says derive two functions such that derive two functions f and g such that h of x is fg of x. The question gives us that h of x is equal to 5 divided by 2 times bracket, it's equal to 2 times bracket 2x plus 1 all cubed. So it's 5 times 2 times bracket 2x plus 1 all cubed. That's the composite function that we have. Alright, so if we're working out this right here, so 5 divided by 2 times 2x plus 1 all cubed. So we need to find now, we need to derive the two functions. So what we can do is, you see all of this 2x plus 1, call all of this y. So call that y, right? So what we're getting is 5 divided by 2 times y cubed, right? And then now what you're going to do is let this y be equal to g of x. So if y is g of x, right? If y is g of x, then what we have then is that this function is really 5 over 2 times g of x, all cubed. G of x, all cubed. That's what we'd have. And so if you were to then replace g of x with a x, what we would actually have is 5 divided by 2 times a big X all cubed. So calling g of x big X. And so this right here is now your f of x. And so that is now your f of x. Alright? This is now your f of x. So your f of x is 5 over 2x cubed, and your g of x is 2x plus 1. So we can conclude that your f, derive the two functions, your f of x is equal to 5 over 2x cubed, 5 over 2x cubed, that's your f of x, and your g of x is equal to 2x plus 1. And that would give you your h of x. Alright, so that's how you derive two functions given a composite function. Alright. Now finally, the next thing we want to look at is finding the inverse of a composite function. The inverse of a composite function can be difficult to find, but it's very easy. To find the inverse of a composite function, this is how they generally write it. Fg inverse of x, and that's equal to g inverse f inverse of x. Alright? So let me write that down right here a little more clearer. So this is how they write the inverse of a composite function. Fg is a composite function, and so fg to the minus 1 of x, this means the inverse of the composite function f times g, and it's equal to g inverse f inverse of x. So to find the composite function, we have to find the inverse of f and put it into the inverse of g. That's how we find it. Alright? That's it. So here it is, fg to the minus 1 is g to the minus 1, f to the minus 1. So you put f to the minus 1 into g. Alright? So here what this question says, given that f of x is 3x plus 3x minus 5 and g of x is 2x plus 1, show that fg to the minus 1 is equal to g to the minus 1, f to the minus 1. So we're pretty much going to prove this right here. Right? We're pretty much going to prove that the formula is right. So this is all we need to know. So the question said that f of x is equal to 3x minus 5. F of x is 3x minus 5. And g of x is equal to 2x plus 1. G of x is equal to 2x plus 1. And what we need to find is, we need to find f inverse x and g inverse of x, and verify that g inverse f inverse of x is fg inverse of x. So first we need to find what is fg of x. xy plus 2x is equal to 4y plus 5. So now since xy plus 2x is equal to 4y plus 5, what we need to then do is, alright, so we need to make y the subject, so we can bring over things that have y on one side, so we can bring over y over here to get xy plus 4y, and that's going to be equal to, bring over the 2x over there and we get 5 minus 2x. And so if we can factorize out y from these two right here, what we're going to be getting is y in bracket x plus 4, y times x plus 4 is equal to 5 minus 2x, right? And so if we were to bring this up here now, we're almost finished. If we divide both sides by x plus 4, we're getting that y is equal to 5 minus 2x divided by x plus 4. Then finally, step 4 is to say that f inverse of x is equal to 5 minus 2x over x plus 4. F inverse of x is equal to 5 minus 2x over x plus 4. And that is f inverse of x. And then that's it, right? And that's how we find the inverse of function. All right. So now let's go ahead now and look at, the next thing is to look at composite functions. So what is composite functions? The composite function does mean a function inside another function. So the composite function fg of x means g of x followed by f of x. That is, we apply g of x, then apply f of x. So in the case where we have fg of x, g of x is known as the inner function and f of x the outer function. And so put x into g and then g of x into f. That's what we mean when we say fg of x. So here's an example. It says f of x is 2x minus 1 and g of x is 3x plus 2. Find g f of x. So to find g f of x, this means we put f of x into g. So we put f of x into g. So what we have is g of x is equal to 3x plus 2. G of x is equal to 3x plus 2, right? Think of g of x as a big x, right? And so now we need f of g of x. So we need f of g of x, right? F of g of x is really like we have our f of this big x right here. F of this big x, right? And f of this big x will be equal to 2 times a big X minus 1. But then what is this big X? This big X we said is g of x, and g of x is 3x plus 2. And so f of x is 2 times what is our big X? G of x, which is 3x plus 2. So we get 2 times 3x plus 2 minus 1. And so this works out to be 2 times 3x, which is 6x, and then 2 times 2, which is 4. So we get plus 4 minus 1. And so what we get is 6x plus 3. And so that is the function now that represents fg of x. And so this is the not fg of x, gf of x. Gf of x. Alright, and that's composite function. So this just means oh, my apologies. This should have been written find fg of x. Find fg of x. Because here it is that I was working on fg of x. Find fg of x. Right? This is supposed to be fg of x. Now what if I ask you to find gf of x? We're going to do that too then. Let's find gf of x. But this question should have said fg of x. So this is fg of x. Now what if I ask you to find gf of x? Right?